Okay, now let's go to the plasma etching. Okay, plasma etching first, chemical etching and wet first wet etching and dry etching. What's the advantage and disadvantage? That's no, correct? And talk about plasma etching. Okay, what is selectivity? How to calculate selectivity? Okay, what is the directionality? How to calculate the degree of directionality? Okay, okay. This one you don't have to remember. I'm going to give you equations. Actually, you see total equations. You are going to require you to remember less than 10. Actually, less than 10. And those equations are very straightforward. Okay? Like for this one, as I told you, even for this one, H selectivity, you don't have to remember. If I'm going to test you, I'm going to give you the equation. Okay? Selectivity and directionality. Okay, and first degree of anisotropy. What is anisotropy? What is the directionality? What is the direction? What? Okay? And then we talk about the plasma. You have to know what is plasma. Okay? In a plasma, what is the mixture of the gas? Okay? What are the components in the plasma? How do we generate the plasma? Okay, in the plasma there are two important processes. The first one is physical bombardment. Second one is chemical etching. Correct? Which one is responsible for the physical bombardment, and which one is responsible for the chemical reaction? In plasma, we have ions which are accelerated, okay, by the shields. You have to know what is shield, right? What is shield? Sheath. Okay, because there is near the surface of the substrate, there is a potential drop. That one is used to accelerate the ions. That's why in charge of the physical bombardment. For the chemical reaction, is because of radicals. Radicals there is no charges in radicals, but it's very reactive. Okay. And okay, this one you see. This one you don't have to know the right equations, but you know that how with the high electron energies, high energy electrons can break the bond to form the radical. Like fluorine radical is typically used for etching of silicon and silicon oxide. And you have to know that the byproduct has to be volatile, okay, in order to have good etch of the material. And sticking coefficient, okay, sticking coefficient, you have to know the concept of sticking coefficient, but you don't have to remember this equation. I will give you if I'm going to test you. Okay, sticking coefficient. And the chemical etching, you know that chemical etching is isotropic, correct? Chemical etching is isotropic, but physical bombardment is anisotropic, correct? And here you know the formation of sheaths. You have potential difference near the surface. And here I talk about the plasma etching, and it's this one you can see if it's pure chemical etching, it's very slow etch rate. If it's pure physical bombardment, it's also very slow. But if you put them together, it will enhance significantly. And it cannot be explained by linear etch model. And why? Because you know when you hit the surface, when you use bombardment to hit the surface, you basically increase the temperature. You make it more energetic at surface. The other one will enhance the chemical reaction. So it's synergistically process of these two instead of just independent process. Okay? And you know how to enhance the directionality. You know, you have to know how to enhance the directionality. Okay, if I give you some H, I say I give you some plasma, let's say some gas. Okay, I say that in order to enhance directionality, okay, what we can do. Let's say I want to enhance the selectivity, what method you can do. Okay, like for example, how to enhance the directionality. First one, you can enhance your physical bombardment. As I told you, physical bombardment is the one for the good directionality, correct? radical H is more chemical, so you will not give me good directionality. Another thing is called inhibitor formation, correct? But of course, after the etching process, because you have inhibitor as surface, you need to do some process to clean it. Okay, the reason for inhibitor because you formed here, and you formed here in this direction because of ion bombardment, you etch of them away. By the surface, you cannot etch of them, so you protect the etch at the side walls. Okay, so understand? And okay, so you don't have to remember this one. No need to remember the equation here. Okay? Linear etch model only applies when the processes are independent. The processes are chemical etch and the physical etch are independent. Okay? But if they are synergetically, okay, synergistically, okay, then it's not. I always cannot pronounce well this one. Synergistically. Okay, for the 4 plasma etching system, okay, you don't have to escape. Okay, already you see so many things. Okay, I already told you last time, right? Skip all these details of the different systems. Okay, but you have to know the etching, some micro-trenching redeposition, and charging and ion path distortion. If I'm going to give you some shapes of the etching, I say please explain what could be the possible issues. You have to know what is the possible reason. Okay? So these are all these non-ideal factors, non-ideal cases during the etching. Okay? And so this is a very detailed description of the whole plasma etching process. Okay? And so you have to know the what is loading effect, correct? Non-uniformity. What is loading effect? Microscopic loading and microscopic loading, and aspect ratio dependent etching, correct? So how to explain if you see the different etch rates, the different patterns, for different aspect ratio, you have to know what is the reason that leads to the aspect ratio dependent etching. Okay, this one I spent some time. Then we talk about the details of etched silicon oxide, silicon, and aluminum. And you know that for aluminum etching is difficult to be etched by fluorine because Because the byproduct is non-volatile, has very high melting and sublimation temperature. So we normally use fluorine to etch it. But for silicon oxide etch, we use fluorine. But for silicon etch, we use fluorine and chlorine both okay. And then we talk about etch of silicon oxide and silicon. We talk about add oxygen. Add oxygen, what's the effect? Let's say if we use CF4, now add oxygen inside, what's the effect? We add hydrogen, what's the effect? And what's the reason? I also explain to you, look at this graph and look at this etch rate as a function of hydrogen percentage and why the silicon oxide decrease is not so significant, but the silicon etch rate decrease is so significant. And what is the reason? Correct? So if I'm going to give you a process, I give you a requirement. Please tell me how to choose your recipe such that you can achieve certain things. For example, I want to achieve certain directionality, I want to achieve selectivity, I want to achieve certain good etch rate. I want to achieve both good etch rate, good selectivity, and directionality. What recipe you can choose? Okay, how to use them instead of just memorizing them.